Good evening, everyone. Welcome to this session on data science. In the last class, we tried to take up a kind of a case study where our objective was to predict whether there would be some kind of a default or a no default on the data, right? So we started doing all kinds of descriptive statistics based on that various aspects with respect to the handling the missing values, identifying the outliers, visualizations, etc. And we moved towards we started talking about data pre-processing, right? So we'll continue from there today. Some of the aspects. We can't access the module for yesterday's class. Okay. Let me see what could have been the problem. In the meanwhile, I'll just move forward. All right. Apart from that, I'm not seeing any other event. So I'm just posted it and you can confirm it. Okay. So once we have visualized the data, right? Once we have done the basic cleaning of the data, we said we are going to do some kind of data pre-processing, right? So on that data, we would be doing some kind of data pre-processing. Now, okay, I think I might have, while sharing, I might have made some mistake. Sorry for that. Okay, so we are doing some amount of data pre-processing. So initially, it's always better to rename the target variable as 1 and 0, whatever are the values that are there. Especially whatever is the event that is of interest to us, we'll make it as 1. The other non-event, you can make it as a 0. Then you are separating the feature variables from the target variable. You are separating the feature variables from the target variable. So you are dropping the target column and assigning all that to X. You are keeping the target column. You are only taking the target column and assigning that to Y. Then you are maintaining a list of categorical columns separately and numerical columns, because this is where we are doing the categorical variable encoding. We are going to convert the categorical variable into a numerical variable. So overall, we are planning to do a one-hot encoding. So for all the categorical variables, we will convert them into numerical by using one-hot encoding. So I'm using the pd.getDummies function from the pandas library, and the entire X, right? Whatever are the categorical columns that are there, right? So whatever are the categorical columns, I am prefixing, I'm separating the column name. Probably if you really look at the columns that got created, you could talk about the columns that got created. You see here, they are typically called as gender joint. So gender is coming up because gender joint. Why is it coming up? Because I am first saying categorical column is the name of the prefix. So gender is the name of the prefix, right? And I am putting up a separator underscore. So gender underscore. Then the actual value columns name values are typically coming up following that. So this is the kind of a notation I wanted to give. Then we said drop first equal to true, which means the first observation would be dropped, where and that would be treated as a part of the default. So this is one thing that we have done. Then the next step is split the data into training data and the testing data. Generally, here this function train test split, it actually gives four outcomes. One is X train, X test, Y train, Y test, based on your X and Y. So X will be split into training data and testing data. Y would also be split into training data and testing data. The size of the test data is 0.3, which is like 30%. So randomly, so and just to replicate the randomness between you and me, we are using a random state. Random state is like a seed value. We are setting, so though we are saying random, we are creating a kind of pseudo random number here. So all of us will get the same set of training data and testing data. Though we are using the word random, it is a pseudo random, because of which all of us will get the same training and testing data. Okay, so that's one aspect. Then we are just capturing the names of the columns, because it is very much possible that at a later point we may delete some of the columns by doing some kind of feature selection processes. So if we are deleting the columns, then appropriately the column names also need to be deleted. So that's the reason we are capturing the names of the column. So if required, I can just quickly look at what is there in the testing data, what are the observations that are there, and what are the observations that are there in the training data. This is just for a display. Then I think we have come to this step where we are talking about feature selection. So we know right now, after I have actually done the dummy variable creation or categorical variable encoding process, I see that there are a good number of columns. I think 39 columns are there in the data, right? So possibly sometimes what we may feel is, are all these 39 columns really useful? Or typically, can some of them be knocked out? So that, because if all 39 columns have to be used, unless they are really useful, there is no point in really including all of them into the model, because that would increase the resources in terms of hardware and time. Okay, separating part for testing and training data are not under. See, basically, okay, think of it like this. Now, we are building a model, or by one model, we'll build 10 models, right? So, when we are building 10 models, 10 machine learning models or something, if we are building statistical versus machine learning, let's say we are building a combination of the model. So it might very well happen that I need to have some common base for me to evaluate. See, most of the times, I think this is something which we have discussed earlier also. Let's say I'm teaching you something on this data, and if I have to test you, if I give you the same data and test you, it is very much possible that you will mug up all the analysis that I have simply spoken, and you will write out the same analysis and you may score much higher. the real learning of you will be known only if I test you on a new data or a new question paper altogether, right? The same logic goes to the machine also. The performance of the machine will be much more better before I roll it on to the production data. I would like to test the model that I have created on some other new data, but I cannot directly put it on the production data. So that is where what I am saying, whatever data that is already available with me, I will save a portion of it, probably 25% or 30% of it. Randomly, I will set it aside because I have a good data, 5,000 records are there. So out of them, probably I will set aside some 30% of it. I think some of the records got removed because of missing values and all, but whatever it is, if I am saying I have a 4,500 records, 30% of it I will set it aside for testing purpose. The remaining only I will use for building the model. Now that same 30% of that data will be used to test all the models. But that data is not used to build the model. Right? That data is not used to build the model. That data is used only to test the model. Now, it's quite obvious that any model that performs well on that data will be the most successful model. And that's the reason we think of splitting the data into training and testing. Does that answer your question, Dev? Okay. So some of the things in a feature selection, obviously a feature selection is one of the most important aspects with respect to building any model, because right now we have 39 features altogether because we have created a lot of dummy variables. So there could be a good number of features involved in the model. Now we really don't know whether all the features are really important. Are they contributing? Are they not contributing? So we really don't know what is happening with respect to various features in the model. Right? There are so many dummy variables in the data. So we have to be clear on whether all the features are really important or not. So as a feature selection, we talk about 5 or 6 steps in the whole process. One is if there are any constant features. I mean, if any, if there is only unique value in the entire column, right? So that column can be dropped. So I can use this function called variance threshold. I'll set the threshold value to 0, especially if I want to remove the 0 variance kind of variable. So once you have defined this threshold, we have fitted that to our training data. So here, if at all there is any column that is getting rejected because of this constant filter, you will not get it in the support. Support is the variable that has retained after applying the constant filter. So we are seeing that 39 variables are retained. So it looks like none of the variable is lost after this step. So we are simply looking at not temp in constant filter dot get support. So we are looking feature wise. If it is not, right? So my intention is to understand if there is any value that is typically, if there is any variable or if there is any feature that is having a constant value. So all falses are saying that there is no feature that is typically having a 0 variance all throughout. And we could also see that the support is all trues only. So which means none of the variables are to be deleted under the heading of constant variance. I don't need to delete any of the variables. So I'm retaining all the columns. So if at all I am having some falses here, obviously my column names also will be updated with that. So every time you are removing any column, you also ensure that your column names are also getting updated. Otherwise, probably there will not be a synchronization between the column names and the actual columns that you had. So these are the column names. We have not deleted any of the column with the constant variance kind of a category. So these things actually when you are doing some of these intermediate steps, it gets converted into a NumPy array by doing all these constant filter transforms and all. Your data actually gets converted into a NumPy array. So that is the reason we are converting that NumPy array into a data frame again. We are converting that into a data frame and we are giving the names of the column. So this step you will see after every feature selection step, because the output of some of these filtration methods is a NumPy array. So anything that comes in a NumPy array, again, you will not have the headings and all. So you will have to convert it back into a PD data frame so that you can put the column names, etc. So this is what we have done in the first feature selection mechanism. Then the second feature selection mechanism, possibly you could club the first and the second, but just from an understanding perspective, I just took both of them separately. So you can very well talk about a quasi-constant removal. So it's not a constant, but it is as good as a constant. So only a very few values are differing from the rest. All other, so one value is having a very dominant presence and the other value is very minimally present. So normally what I suggest is you can go with probably a 99.9% of the observations of one kind and 0.1% of the observations of the other kind. Or slightly to be more relaxing, you can very well say 99.5 and 0.5. So in that case, what typically happens is if I multiply, so basically the variance in this case would be P times 1 minus P, assuming a kind of a binomial distribution. So this will become 0.005 times 0.995. So if I multiply this, this comes out to 0.004975. So basically, if required, I can set a threshold of 0.005. So which means whichever observations are 99.5% of the observations are of one variable, I mean one category or one observation, unique observation, and only the remaining 0.5 percentage of the observations are of a different value, especially if I'm talking about dummy variables. Let's say 99.5% of the observations are a 1 and only 0.5% of the observations are a 0 or vice versa. So in those cases, what we are saying is the presence of 1 may not add much of a value to the analysis. So if you are having even very large data, probably you can even think of 0.1% and 99.9% also. Because 0.1% itself, let's say out of 1 lakh records, 0.1% itself could be 100 records. So 100 records is a decent data for some kind of analysis. So probably if your data is too large, you can very well think of 99.9%, and based on that, you can set your threshold to 0.001. So anything, again, it's the same thing. If you look at, the only thing that I changed is the threshold. Now I am looking at some kind of filter. Right now I am looking at some kind of a filter. Again, I'm looking at the support. But this time, right, I'm also looking at the column names, I'm updating. So whichever is there in the support, only take those column names. Now I could see that there is a decrease from 39 to 38. So something has actually become false. Right, in this process, something has actually become false. 9, 9, 18, 8, 26th column was actually false. So probably if I look at here, I mean, because I'm running the whole code, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Total units greater than 2U. Right? We have actually we have merged those and we have kept. But still, I think after merging also, the total count was only 26. Right? 26 out of 26 out of 5,000. I think the frequency could be much lower. So it's just around, I think, 0.52% or something. Right. So that could be because of that. And some of them would have got dropped off. So the number would not have been 26 also. In some of the missing values, removals, etc., this number would have come down even more. So it would have gone probably less than 0.5%. And that's the reason that value would have got knocked out. Right. So total units greater than 2U is actually getting knocked out. Probably in this data, if you see, you would be seeing only total units. No, not the total units. So here you are seeing total units greater than 2U. But probably when I am looking at after the near zero variance, I should not be seeing the total units greater than 2U. You see, I'm only seeing total units 2U. I'm not seeing the total units greater than 2U. So basically, it means that if I have removed that particular column, then here what is happening is it would also be treated similar to the default. So whatever is total units greater than 2U, that would also be treated on a similar lines with the default, because default column is also not there. Total units greater than 2U column is removed now. So what will happen is all those observations which are a part of total units greater than 2U, they would also be treated in line with the default itself. Okay. Then the third thing, so we have removed a constant column, which is like a zero variance column. Then a quasi-constant column, which is like a near zero variance column. Now the third aspect that we are working on is removing the duplicate features. Now this is probably removing duplicate features. Sometimes what could very well happen is I may have a column with name X, right? Probably let me say I may have a column saying gender, and suddenly I'll have another column with name as sex. Because let's say the data could be much bigger with so many rows, so many columns. Sometimes, or probably we may have one column called income, and somewhere else there might be a column called salary, and both the columns might be representing the same set of values. Both the columns might be representing the same set of values with a different, or probably because of some copy paste, the heading would have got changed, but the data inside that column would have been more or less the same. So these are the ones we call as duplicate features, right? So the name might be different, but the content could be exactly the same. So these kind of features, obviously, they will carry a correlation of 1, which is very clear. But sometimes the correlation of 1 can be associated with even different features also. Then the features need not be the same feature represented by two different headings, but they may still be very highly correlated also. But here we are talking about duplicate features altogether. So where all the values, etc., everything are one and the same. Now, what we are saying here is there is a function called duplicated. There is a function called duplicated, which actually returns a value of true, but this is generally applicable to the observations, not to the variables. So it means the rows. So this is applicable to the rows, not to the column. Right? Duplicated is a very good function that is there. So if you really want to remove the duplicate rows in the data, you can very well use this function called duplicated. But here my objective is to remove the columns which are duplicated, features that are duplicated. That's the reason what we say is you transpose. Dot T is nothing but you transpose the training data. Transpose is you are making the rows as columns and columns as rows. So your training data, you are doing a transpose and you are storing it in a variable called xtrain_t. Similarly, your testing data, you do a transpose and save it in xtest_t. So what happens? This transpose is a matrix function. And because it's a matrix function, my data becomes a matrix now, which is like an array, ND array. So matrix is again a format of an array. So we will convert that matrix into a data frame, both of them, the training data as well as the testing data, the transpose of which we have taken. So now you could clearly see my training data is having a shape of 38 rows and 2,828 columns because you have transformed it, right? Now my training data, transpose of the training data is having 38 rows and 2,828 columns, whereas the transpose of the testing data is containing 38 rows and 1,212 columns. Now I can very well look at if there are any duplicated values. Because as I told you, the duplicated as a function will work. The duplicated as a function will work on the row level data, not on the column level data. So that is the reason I have transposed it. So all my columns will become the rows. Now at a row level, I am trying to do the duplicated function. So I am applying the duplicated function and I am looking at the sum to understand if there are any, because it returns a Boolean value. Is it duplicated or not? So if it is true, I can sum up all the truths. So which will give me 0, which means none of the columns are duplicated. But of course, in some kind of huge data sets, it is very much possible that your data can very well be duplicated as well. Some of the columns can very well be duplicated in your data. Okay. Then, so if at all they are duplicated, I can really look at whether they are duplicated or not. So you could clearly see all of them are showing as false. So none of these columns are really duplicated. So if at all we are having some kind of a duplicated, you can very well remove those duplicated features. So you can very well see here, remove the features that are identified as duplicate. So what happens is if there are two duplicates, the first one will still show a false. Let's say these two columns are duplicate. gender joint and gender sex not available. Let's say they both are the same thing, but probably people have given two different names. So then what will happen is the first one will still show as a false, but the second one will show up as a true. And because of which you may have to remove the second one. So again, in a serial order, one of them would be retained and the last one would be coming out with a kind of a duplicate which you may want to remove. Remove the features that are identified as duplicate and retain the remaining one. So basically, what are the features to keep? So I'm first seeing whatever are the index that is in the duplicated features and I'm putting a not. So which means initially they would all be false. If they are in duplicated features, they will be false. And if I'm putting a not before it, they will become true. So I'll retain all the true columns, which means I'll retain all the columns. So features to keep again will be this list. Then I'm also looking at the column names. So whatever are the features to keep, I'll keep all those column names. Right? I'll keep all those column names. Again, I'm reconstructing my training data and testing data. Obviously, after this step also, there is no loss here because there are no duplicated columns. But if there are duplicated columns, there would be a loss of some of the columns in the data after this step. Okay. Okay, let me just look at the. Okay, I mean, I'm just giving from a simplistic perspective. I am also telling you there very clearly that income and salary are filled with the same data. Right? I think you have to follow the statement that I'm making also. I just used an example, income and salary, but I am saying that both of them are filled with the same data. Right? But what you said could be different. Income and salary can be different. Salary, okay. So, but what I am saying is, I have a data where both of them are filled with the same, but with a different heading called income and salary separately. All right. Then the fourth case that I am trying to handle is they are not duplicated columns, but they are very highly correlated columns. They have a high correlation between them. Right? So it might very well be possible. So initially I can think of now all the data is a numerical data only now. Now there is no categorical data because we have already done the categorical variable encoding and we have converted all the categorical columns into numerical only. Right? I've converted all the categorical into numerical. So I can very well take the correlation across all of them. Right? So when I look at the correlation, I could see that because this is a slightly larger data, probably my correlation values are not that clearly visible. But one thing we could see is across the diagonal, the correlation is 1. And probably the more greenish or yellowish kind of a number, there we could see that the correlation is higher. But the more the bluish or this kind of a signal, so we could see that the correlation is very much towards the negative side. Right? So probably here you could see a kind of very negative kind of a correlation as well. Right? Very strong blue. So we can very well see that if there are any columns that they are very highly correlated, we can think of removing them as well. So initially I'm taking a correlation matrix and I have plotted a kind of a heat map with all the correlation. So we have discussed about the heat map earlier. So initially I'm taking a correlation matrix and that correlation matrix I'm converting it into a heat map. So these are the colors that we are trying to put. So then obviously here nothing is that clearly visible. So I'm writing one function where this is a very clear cut function. If you look at it, I am creating a set of correlated columns, right? The highly correlated columns, I am creating a set. So what is that I am saying here? For the entire data, first I'll take the correlation matrix. So just like the way we have done here, right? This is what is your correlation matrix for the entire data, whatever you pass, I would compute the correlation matrix. Now, I am looking at the number of columns in that correlation matrix. So basically, if I represent it like this, so I have my correlation matrix like this. So X1, X2, X3, X4, X5, 5 columns. Here also I have X1, X2, X3, X4, X5. So corresponding to these 5 rows and 5 columns, there is a correlation value. This is what we are calling as a correlation matrix, right? Obviously, across the diagonals, we'll have a 1, and all other pairwise correlations will be shown aside. So what is that? I have computed the correlation matrix. I have a blank set called correlated column. So which columns are having high correlation between them, I'll be adding to that. So I will look at how many columns are there. So obviously in this case, there are 5 columns altogether. So I am looping this for 5 times, right? Now I would go, let's say in the first loop, this is 1. So obviously the naming in Python is 0, 1, 2, 3, 4. So basically when you are looping it from 0, 1, 2, 3, 4, 1, 2, 3, 4, my I is having a value of 0 first, right? So the second step we are saying J is range of I. I is only 0, so J also will be 0 only. When I is 1, J will be 0, 1. Because it is in the range of 1. I is 2, J is in range of I. So it becomes 0, 1, 2. Similarly, I equal to 3, J becomes 0, 1, 2, 3. And I equal to 4, J will become 0, 1, 2, 3, 4. Right? So now in the first loop, only this, I equal to 0, J equal to 0. Then what we are saying, you look at the correlation matrix and look at the location ij. So the correlation matrix, this one, 0, 0. If it is greater than the threshold, so probably I will set a very high threshold, let's say 0.95. If this value is greater than the threshold, so which means this column is having a higher correlation. So what is that I say? Correlation matrix. So in correlation matrix, whatever is the column number is typically the X1. So that X1, I will simply add it to the correlation set here. So for every pair of column, right? For every, so I'm calling that as the correlated column. So whatever is the column that is having the correlation with, I would add it to the correlated column. So basically what we are saying here, let's look at it. Now I could see here, business or commercial NOBC. So this one is actually having a correlation of 1. So I am putting a section of 1. So it looks like this particular variable is having a correlation of 1, absolute correlation of 1, because I'm setting a correlation of 1. So it is actually sharing a -1, looks like. You see, business or commercial NOBC it is having a correlation of -1 with another variable called I don't know, there is another variable. Okay, let me not zoom it. Probably let me count it, and it looks like because there is something that is still going on. So I can very well look at. Oh, okay. I think this time it should be visible. This is having business or commercial NOBC is having a correlation of -1 with loan type 2. Loan type 2, it is almost having a correlation of -1. So, which means they are actually, so loan type 2 would be more or less like business or commercial NOBC. So we are seeing that those two values are actually having right, those two columns are actually having a very high correlation between them. So that is the reason in my exercise, that column is typically coming out as a high variance kind of, a highly correlated kind of a column. So when the correlation between the two is almost 1 or -1, you can very well drop out one of the columns. You can drop any column of your choice because both of them are 100% correlated. So that is one thing that we are doing. So the threshold that I have set in the first case is a 100% threshold. Any correlation, any pair that is having a correlation that is greater than or equal to that kind of a threshold, I can very well get it knocked out, right? So anything that is having a very high correlation above that threshold, it gets knocked out. So we are seeing that business or commercial NOBC is typically having that kind of a very high abnormal correlation, and that is where it is typically getting knocked out. All right. Then the next thing we are looking at is, okay, now after this, again, we'll have to look for that particular label being dropped. So I'm looking at the correlated feature 1. I'm dropping that correlated feature 1, both from the training data as well as from the testing data. So, which means now when I look at it, I should not see NOBC. Right now, in this case, I should not be seeing that column business. So the loan purpose, loan type 2 is there, but NOBC, business or commercial NOBC is not present in the data. So that is the next step. So basically, one is the variables which are duplicated, we have dropped. The second is the variables which are having a high correlation, absolute correlation of either -1 or +1. So in that case, in a serial number, in a serial order fashion, I have dropped one of the columns. Then comes the next step where I'm actually doing a kind of, now it is not -1 or +1. So if it is -1 or +1, one can be randomly dropped. One can be randomly dropped, no problem at all. But if it is not -1 or +1, let's say if it is 0.96 minus 0.97, let's say if the correlations are much above a particular threshold again, let's say more than 0.9, which are less than -0.9, but definitely not -1 or definitely not +1. So they are still a very high correlation, but definitely not a +1 or a -1. So which means I cannot drop one of them on a random basis, right? So if I am looking at the same analysis by setting a kind of a threshold of 0.95, after I removed, obviously now I can see once I have already removed my training data, removed that OBC, I mean the business or commercial and OBC kind of a data. So my training data does not contain that column now. Now I am looking for 9.95 as the cutoff level. So if there are any, I would like to take a call, but now this time I got an empty set. So once I remove that particular column, no other columns are typically having a correlation of more than 0.95, right? So the other way I can look at, if at all there is a high correlation, right? So the best thing is take all the pairwise correlation. So we had created a correlation matrix. Out of that, convert that into an absolute value, because now for me, even if it is a negative correlation or a positive correlation does not matter. So I am taking the absolute value of the correlation. And I am stacking all the correlation. Rather than in a matrix format, I am putting it one below the other. Stacking is more like one below the other. Now, if you see here, credit type CRIF versus loan amount, this is the correlation. Versus term, this is the correlation. Versus credit score, this is the correlation, and so on. So what we could clearly see is uh, these are the pairwise correlation. Now, credit type EXP versus loan amount, this is the correlation. Versus the term, this is the correlation. Versus the property value, this is the correlation, and so on. So versus the gender joint, this is the correlation. Versus gender male, this is the correlation. So we are getting all the pairwise correlations and we are stacking up all the correlations. So all pairs of correlations are visible here. Now ages wise, right? Age 35 to 44 versus loan amount. This is the correlation. Versus the other ages, this is the correlation. So we could clearly see the correlation between each of the columns accordingly. Every pair, we are seeing what is the correlation with the other values. So the entire set of correlations are typically stacked. Then once I have stacked it, I am sorting that correlations in the descending order. So obviously at the top, you could see that loan amount to loan amount, gender sex not available to gender sex. No. So it's a correlation of the same variable with the same variable. Obviously, all those correlations will be one. So we have seen until here, those are the scenarios. But after that, you could clearly see the other ones that are coming in: loan amount versus the property value versus the loan amount. Both of them are having 0.75. That is the highest. Then co-applicant credit type EXP versus the gender joint. Both of them are having around 7.7% correlation. Then region south versus gender sex not available, we had a 0.65% correlation. Income and loan amount is around 0.6. Loan purpose P4 and loan purpose P3, they have a correlation of 0.58. Like that, you could clearly see that some of the categories have a higher. So occupation type PR and occupation type SR are having a 0.53 core. But in all these cases also, it's not that the correlation is that significantly higher than zero point 0.9 or 0.95 kind of a thing. So this is where I would look out for if there is any correlation data that is greater than zero point 0.9. Obviously, in this shortlisting, what would happen is all these ones would be shortlisted, right? Because there is nothing other than this which is greater than zero point 0.9. But these are of no use for me. So that's the reason I'm also setting a rule that the correlation data should be less than 1. So I'm only taking all those correlations that are between 0.9 and 1, but 1 is not inclusive. So I'm only looking for those. Obviously, here it has come out as an empty series for me because I don't have any series that is having a correlation of greater than 0.95 but less than 1. So now what is that we are doing? I would be getting the pairs, whichever are highly correlated. I would be getting these pairs. Let's say if I had set 0.75, then I would have got this particular pair. Instead of 0.9, let's say I would have set this as 0.75. You can try this out in case you want back home. Right? I would have got this pair, loan amount, property value 0.75. I would also got property value, loan amount 0.75. So these two lines, these two rows would have got shortlisted. And if I had set 0.7, then probably these 4 rows would have got shortlisted after this step, right? Then I am creating these 4 as a separate data frame, right? Because I'm not running it now because the program is still running, right? I am just trying to explain you what is happening, right? So the complex models, they are still running, looks like slightly below. So I am converting that into a data frame, all 4 columns. So these 4 columns will be available to you, and I'm calling them as feature 1, feature 2, and correlation value. So these are the names that I'm setting to those. So basically now I would be having feature 1, feature 2, correlation. And if I had set it to 0.7, I would have typically got this loan amount, property value 0.75, property value, loan amount 0.75, then co-applicant credit type EXP versus gender joint 0.703. Similarly, gender joint co-applicant, this EXP, this is also 0.703. So this is the data frame that would be available. Now, what is that we are saying? Look at the correlation data. I would have got those 4 columns, but here, because I have set 0.9 as the cutoff, I'm getting a kind of empty column. So my data frame only has the heading. It does not have any content inside. Then we are going for groups of the correlated features. Now what we are trying to do is we are trying to group all the correlated features. So what we do in grouping, because the intention is it might be possible that these two are correlated in one way, highly. Probably that's the reason we choose 0.9 or 0.95, right? Probably for time being, let's assume that this is 0.953 for time being. And probably let's assume this is 0.943, right? This is 0.953 and 0.943. So what is happening, and probably it could be possible that loan amount with some other variable, loan amount with some other V2 variable is also having 0.93. So what is that we are trying to do when we are trying to grouping is, we will start with this F1, right? So for features in feature 1 dot unique. So we are taking all the unique values here. So you will go with LA, PV, CACT, EXP, GJ. These are the unique values. So we are starting with these four. If feature not in the grouped features list, grouped features are, we are creating groups. So if the feature, whatever we have started off, so let's say initially we started off with LA. LA is not, when we start, there is nothing in the grouped features list. So with the LA, what is that we are going to look at? We are looking at a correlated block where if that feature 1 is equal to the feature. So whatever the feature, so I will look out for in this table wherever LA is there. So these are the two places where LA is there, right? Then whatever are the ones that are associated with LA, I will put all of them into one group. So basically it is like LA, PV and the V2. These three are put into one group, right? So we have created a grouped features list where we already have, right now we are starting with a blank one, but we are adding these three to that grouped features list. So then again, I will go to the second PV. Okay, for PV, there is an LA. So PV, actually PV and LA are in the one group, should be in one group. So PV and LA are already there here. So I'll ignore this. Are already there in the same group. Or probably if I say there is one more PV and if there is a V3 with minus 0.94 kind of a number. So when I'm starting off with PV, I see that the groups are LA and V3. All right. So PV is already added to one group. LA is already a part of that group. So then we are saying V3, add the V3 also to this group. So like that, we will try to keep adding the groups. Now let's say the next group is CACT, EXP. That is what? So for that, the pairing is only with GJ. So these two, and so which means they are not there as a part of this group. None of them is a part of this group. So this would be one group, this would be the another group. So what is that we are saying? All the highly correlate, because some pairs could be very highly correlated. Not necessary that all of them are correlated, right? Probably X1, X2, X3 are correlated among themselves, but they don't carry any correlation with X4 or X5. Similarly, X4 and X5 alone could be highly correlated, but they may not have any relationship between X1, X2, X3. So to identify that, what we say is go with this correlated features grouping. Obviously, in this case, we will not have any group. But what the intention is, for each, so all the variables within that correlated group, they are very highly correlated. They have a very high correlations between them. So whatever we set as 0.9 or something, that is the threshold that we have set. So within that group, we are seeing a lot of variables with that kind of a threshold. So are more than that threshold. So obviously, all of them, I mean, I should not include all of them. So probably I should, if I include only one of them and remove the remaining, let's say in this case, the 4 variables are forming one group. In this case, 2 variables are forming one group. And all of them are having greater than 0.9 among them. Here also greater than 0.9. So what we say here is, out of these 4, just retain 1. Out of these 2, just retain 1. Remove, drop the others. Now, I can't drop any random. If it is -1 or +1, I can still do a random drop. It does not matter much because it is 100% taken care of by the other variable. But here it is 0.9596 kind of numbers. So I cannot drop any way, all the variables in a randomized fashion. So that is where we are first trying to identify if there are such kind of groups. Obviously, here you could clearly see there is no such kind of groups. But I have taken an example. If I would have given a 0.7 as a kind of a cutoff rather than 0.9, I would have got 4 groups, four correlations. Out of them, I would have got 2 groups. One is with the income and the loan amount and the PV. And the second one would definitely be CSVT versus the GG. Now, each group, we have 3 elements, 4 columns, 4 variables in each of the groups, right? So you would try to identify which variable is the most important variable out of those 4 variables. So this is where we use an important mechanism called feature importance using a model, right? So you could do a lot of other things as well. But here we are trying to look at the feature importance using a kind of a model. Though we did not discuss about the random forest till now, but here I'm just using that random forest. So I will simply say, if for each of the group that is there in the correlated group, so we will get 2 correlated groups list. So I will pick the first group, right? The first group contains 4 elements. As per my definition here, LA, PV, V2, V3. These are the 4 elements, 4 features that are there in the first group. So we are looking at the list of the first group versus the list of the second group unique features. Then we are building. Now only those features we are taking. So which means I will take my target variable right now is having either a 0 or a 1, which is like a default or a non-default. And I'll have 4 columns. One column is LA, the other is PV, the other is some V2, the other is V3. These 4 are a part of. So I will have, this is the new subset data that I'm having, right? So I would take that, and on that data, I would typically create a kind of a random forest regression model. Why random forest? There is some advantage with this. Random forest is a, when I discuss about it, I'll explain it in more detail. It's an ensemble based model. So which means it tries to handle some kind of overfitting, etc. And it also gives, it has a mechanism of giving what is called as a variable importance. What is the importance of each of the variables? Though some other algorithms also give, but probably this has been the most popular from that perspective. So it gives something called variable importance. So what we are saying is, I will fit a random forest by taking these four columns as the predictor or feature variables, and this column as my target variable. Based on that, I am trying to do a random forest fitting. And based on that, I am trying to understand what is the importance. What is the importance of feature of each of the features? What is the importance value of each of the features? So you could clearly get based on this, we are keeping a kind of a tabulation, right? We are keeping a tabulation on what are the feature and what is the importance of that feature. So we are clearly sorting all the values by the importance. And whichever comes as the top importance, I log of 0 is nothing but the first location. So in the importance, whichever out of these four, so for each of these four variables, I will compute the importance by using the random forest algorithm, right? So, and I will sort the importances. Whichever one is having the highest importance, I would be taking that column. So let's say here V2 column will have the highest importance out of all these four. I will knock out all these four columns. I'll retain only the V2 column. Similarly, in the second iteration, I will look out for my target variable versus the two other this thing. So using them, I will build another random forest model. I'll try to do a variable importance again for those two variables. Whichever one comes out to be the highest, again in that, I will be selecting them. So which means if I have two groups, I will get two variables. One from each group, one variable will be selected and all the other variables will be knocked out because they have a very high intercorrelation between them, and it might very well cause a kind of a huge multicollinearity effect. So this is a very, very important step. Many times people ignore this step very easily because it's a slightly difficult step to implement. In one of the solutions that I have implemented in one of my consulting assignments, we had to write this piece of code, right? And probably this at that time also this has been picked up from some other source itself. But this is a kind of a very extraordinary step, I can say, because here highly correlated features in groups, especially if you have a too large volume of a data with so many columns, what you would very well find is they are very much clustered by groups. So you cannot remove all the columns, you cannot retain all the columns. So the best thing that has been suggested in the literature is try creating the clusters of columns which are having a very high correlation, let's say above a specific threshold. And out of them, from each of the groups, identify which variables are the most important variable with respect to the target. So this is this kind of a mechanism, random forest based classifier mechanism, you can use on the entire data also, right? You can use it on the entire data also, and you can identify the feature importance, and you can the other day, if you remember, I was talking about feature selection. Feature selection, which is an algorithm driven feature selection. So this is what is that random forest algorithm driven feature selection, right? So what is that? You will simply say, you will take all the features. These are your x's. You have your y, which is your target. You directly fit a random forest algorithm between the two. And based on that, so these are model driven. These are model based or model driven kind of feature selection. I can directly find out the importance of each of the variable, and I can retain the top few features and knock out the remaining features altogether. So that way, The random forest kind of an algorithm can be used in feature selection also. But this is a kind of a wrapper method. It's not a filter method because wrapper methods are all model dependent. Here I'm using the random forest kind of a model to try to identify the top few features and knock out the remaining features. Okay. So through that, I can very well say that these are my important features. So obviously here we did not have any such kind of a story. So it looks like the important features are simply kept as black, right? So you can very well take the data frame of the important features. Obviously in that case, I could have got V2 and let's say GJ. These two would have come out as important features, right? So when I'm printing the important features, it would have simply printed V2 and GJ. So then we are saying that those are the two features that needs to be considered. Those are the two features that needs to be considered. And features to discard. So we have already got our correlated features one. I have got the list of all my correlated features. Where are my correlated features? I have got my list of all the correlated features. Where did I put correlated features one? Okay, so we are getting all of them that are more than 0.95 or probably we have to be consistent. So we should put more than 0.9 rather than 0.95 because there also we are putting 0.9. So these are the list of my correlated features. So out of those correlated features, I am removing the features to consider because out of them I'm shortlisting two or three features. One is V2, the other one is uh, GJ. So I'm shortlisting those two features. Remaining all can be discarded. Out of all those correlated features which are having correlation more than zero point 0.9 or 0.95, be consistent. So you can retain those some of the features which we have got in the process, and you can discard all the remaining features. And based on that, you can compute you can recreate your training data and the testing data. We could see that now one column got reduced now because that was primarily in the last step where the correlation was 1 or -1. That column, business or commercial NOBC kind of a column got dropped. So now after this step, we are still left with 37 columns in the data. So are we clear until this step? I'll take a small pause because it's a slightly complex logic that we have put. So just want to understand if there are any queries so that I can handle them before I really move to the next aspect. Anyone, any queries in terms of feature selection? Because feature selection becomes a very prominent topic that we generally work on. Yeah, we'll see once more. Okay. So the same, basically, what I suggest is to understand it little bit more method because right now I could have run it, but I'm running some random forest algorithm. I mean, as a part of the models. So I wanted to. I've put some kind of hyperparameter selection and all those things. So which may take a few hours to run. So I don't want to disturb it right now. So that's the reason I am not able to run them. But once I give the code to you, probably you can set this to 0.5 or 0.6 so that you will get some pairs, right? This one also you can set it to 0.5 or 0.6. And even here you set it to 0.5. But in general, you won't delete like that, right? In general, the deletion happens only with 0.9s and 0.95s only, right? But just to understand, because not many data in some of the data you may not get those. But here we have got that one plus one or minus one. We have got one field, one variable with a minus one kind of a correlation, and we had to directly remove that column altogether. Okay. Then just give me a minute. I'll just grab a glass of water and come. Okay. So we are done with 4 major variable selection mechanisms. One is zero variance. The second one is near zero variance or quasi-constant. Then we also looked at duplicated features. We removed. So all these are in a kind of a serial fashion. So sometimes what you can also do is you take another data set altogether, and you can even experiment all these things on that data set, and probably you can come back to me saying where the code is not working also, right? Because sometimes when you are working with a totally new data set, there might be some kind of errors that might crop up when you are just replacing the data set with some new values, or right. So basically this is a kind of a continuous improvement to the code. So on one side we are learning, and on the other side we are also taking away a kind of a reusable code, which probably we can work it out on our day-to-day data as well. Then we also talked about highly correlated features. Highly correlated features are the ones which are typically with a -1 or a +1 kind of a correlation. Or we are also talking about the highly correlated features with, let's say, greater than 0.9 or less than -0.9. So in this case, you can randomly remove one of those two, because both of them are meaning one and the same. Whereas highly correlated, greater than 0.9 or less than -0.9, in this case you cannot remove randomly. So that's where what we create is, we create groups of variables which are having point greater than zero point 0.9 or less than minus zero point 0.9. We create two different groups, and under each are n number of groups which are having highest, more than zero point 0.9 absolute correlation between them. And then out of them, for each one, we would typically measure which within each group we will try to find out which observations are or which variable is a most significant variable, highly importance kind of a variable compared to the others. You retain that one variable and you will lock out the remaining variable. So that is also a kind of an exercise. Sometimes people ignore that exercise, but that can very well lead to a especially, see, in some cases you can handle it through principal component analysis. Whereas in some models, especially the tree-driven models, etc., that might very well be a kind of a showstopper as well, because it might very well be possible that some variables would be included and some would not be included. So as a practice, it is always better not to have too many variables which are highly correlated as a part of the model. Then the next step that we are bringing in is, so you can select the features we have discussed the last time. You can very well select the features based on a chi-square test, or based on you can very well select based on a model, or you can try to link. You can try to find out the relationship between your dependent variable and the independent, which is like a target variable and your feature variable, right? So one of the ways to look at it is you try to find out a chi-square test. If you know, the chi-square test is nothing but it's a test of independence. So I am looking at every dependent variable or every feature variable versus the target variable. So I try to find out the chi-square test between the feature variable, every feature variable, and the target variable. So if I'm doing the chi-square test, you could see here. So it is typically giving, so this part is the coefficient, the chi-squared coefficients, and this part is typically the p-values. So we have the chi-squared coefficients and we have the p-values. I can very well plot the p-values. So I'm collecting the p-values for all these. So you could see that in some cases the p-values are very much zeros, right? Whereas in many cases the p-values are much greater than 0.05 as well. So the chi-square test is talking about the test of independence. So which is also saying, so if I'm plotting the set of p-values, which means you could clearly see that if the p-value is greater than 0.05, it is coming out that the feature variables that you are considering, they are not having a major role in predicting the target variable, right? So here, if I'm looking at the chi-square, probably let me take you through that chi-square. So you could clearly see here, it is computing the chi-square statistic between each non-negative feature and the class target variable, right? So it is actually using the score, whatever it is computing, the chi-square score, it is used to select the n features with the highest value for the chi-square statistic, which means the lowest p-values, right? So those features can be included and the remaining features can be knocked out. So you can possibly, if there is a formula or something, I don't think so. So this is again a kind of a univariate feature selection mechanism. So you can use chi-square, you can use F-test based classification, you can use mutual info based classification. So we have already discussed mutual info based classification is a non-parametric model, but F and chi-square. So you could clearly see if a chi-square test should only be applied to non-negative features such as frequency. So in our data, we don't have any kind of a negative feature. So that's the reason I can use a chi-square test, right? So all these, the methods based on F-test estimate the degree of linear dependency between the two random variables. Mutual information method can capture any kind of statistical dependency because I said it's a non-parametric method. It's a so it can capture any kind of a non-dependency. But of course, you require more and more samples for working out with it. So you can use all these three testing methods. So that is where I started off with the chi-square, right? So with that chi-square test, I am getting all the p-values. I'm sorting the p-values in the ascending order because I want the lowest p-values. If the p-value is the lowest, obviously the chi-square statistic will be the highest. So you could clearly see that this chi-square statistic is very high. The p-value is 0. P-value is almost 0. P-value is almost 0. 0. P-value is less than 0.05. Less than 0.05. Less than 0.05. This is also less than 0.05. It is 0.02. This one is less than 0.05, but this one is not. It is 0.22. It is greater than 0.05. This is less than 0.05. So we are seeing only a few, all are 10 to the power minus 1s. 10 to the power minus 1s are definitely greater than 0.05. Right? Even this one. So there are a good number of variables which are having a p-value of 10 to the power of minus 1, which are all greater than 0.05. So I could clearly see when I have plotted the p-values, I could clearly see that some of them are very, very high p-values, right? Almost close to 1.9 kind of numbers are there, right? Probably you could see this one, 9.2 into 10 to the power minus 1, which is like 0.92 kind of number. So we have some point. So those kind of big numbers are also there. You see, this is 0.97. So some of them are having a very high p-value. So which means you could clearly say that these variables are completely independent. So I am trying to find out the amount of dependency between the two variables. And I could clearly see that p-value is very, very high and the chi-square statistic is very, very low, which means I can easily knock out those variables altogether. Now, using this mechanism, if I am seeing p-values I need only for less than 0.05, suddenly my problem has dropped. You see, my problem has become a very simple problem. Now my number of variables have come down drastically. Now my model has become a very simplified model. Only how many columns now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 17 columns, 17 variables only are there. 17 feature variables only are there. We started off with 39. But once we are, so I did not execute any model till now. Of course, random forest I had to use only for if there are grouped correlations between the various data elements. But in that also nothing got lost right now. But once we do this exercise, the chi-square, you are able to see that a good number of columns are getting knocked out, right? So you could very well look at. We can very well drop out those columns also, right? I'm just creating as a separate. I'm creating as a separate table altogether. Xtrain underscore p and xtest underscore p. But typically, I mean, after that, again, I should have simply continued with xtrain underscore p. But I think here I'm continuing with xtrain only. So that's where I think you may have to modify this, right? Because based on the chi-square, my new data has actually become xtrain underscore p. So even here, I should keep working on xtrain underscore p. I should not work on the original xtrain. So that is where I think a correction can be made. But right now I'm not making that correction, but I'm informing it to you. Then the next mechanism that I can use is the mutual information, because we said I can use an F-test based mechanism, I can use a mutual info, and I can also use the chi-square. So it's always better to use at least one or two of those, so that only the most important variables will be retained and all others can be knocked out, right? So possibly in all these steps, we should work with xtrain underscore p. If you have understood the logic correctly, we are not working with xtrain now. We are working with xtrain underscore p, because the p values greater than 0.05 have been knocked out in the chi-square test. So otherwise, I'll make a change, right? Probably I'm not running it now, but I'll make the change xtrain p, and we are using the mutual info. Mutual info based classification is what we are using. And I am trying to find out the mutual info on xtrain p only. I'm not using xtrain, but of course here you will get the result for xtrain. Based on that, I'm going to get the mutual info. Mutual info, we have said it is basically, if I put up this mutual info, so you could clearly see in case of mutual info, this is the one. So you will typically take probability of joint occurrence of x and y divided by individual probabilities. You take the logarithm of that, right? And you multiply it with the joint probability of x and y. And you sum across all the x's and all the y's. So this is what is called as a mutual information between x and y. Now what is happening? Just assume if these are completely independent, right? If x and y are completely independent, probability of joint probability is nothing but, if for independent event, joint probability is nothing but the product of their individual probabilities. Right? P of x intersection y is nothing but P of x into P of y, especially when we are talking about two independent events. So in that case, this whole ratio will become 1. Log of 1, which will become 0. 0 multiplied this is going to be 0. So across all the x and y, you are going to get a 0. So if at all we are saying that the two are independent, we are going to get something which is very close to 0, right? Whereas if you are looking for highly dependency between x and y. So obviously here your numerator will be lesser than the denominator, right? If you are talking about p of x comma y, your numerator will be lesser than the denominator. So this ratio will be less than 1. Log of a value less than 1 is a negative value, right? Log of a value less than 1 is a negative value, and you are multiplying that with a probability, and you are adding across. So that is what is typically coming out as the mutual info score, right? So you can very well look at your mutual info score, and you can very well look at the p values that are coming. No, you will look at your mutual info score value. So if the mutual info score again is kind of negligible or lesser than a particular, because if it is going more and more closer to 0, then obviously all those variables will be useless variables. But of course here we have already eliminated some of the variables using our chi-square test. Now we are trying to eliminate the remaining variables, but of course, because I had used x underscore train earlier, it has considered the entire data. But if you consider x train underscore p, it will only consider the new data only. I mean, after removing some of the variables. So you could clearly see that some of the variables are having a decent mutual info value, but there are so many variables with a 0 and which are almost negligible. So you could see that there would be some cutoffs also that you can define. Okay, I don't think it is straightforward. So possibly we have also, let's say we can set 0.0001. So which means 0.0001 means all these would get knocked out, right? So all the remaining things are greater than 0.0001. But of course, I should not do it on x underscore train. I should do it on x train underscore p. So out of those 17 columns that are retained, I will be seeing which ones to be removed. So if there is now we may not know if there is any other variable to be removed, or all those 17 might be retained as well. So I would again continue this x train, or probably if I call it as x train also, here it should be x train underscore p, right? So this would be my new. So I would again take it back so that I don't need to redo the next steps. So I'm taking x train underscore p, and I'm selecting all those columns that need to be included, and all the other columns I'm deleting. So this is one more filtration that I'm doing. So which means I'm only retaining those columns which are really, really important. I'm not working with each and every column. I'm only retaining those columns which are very, very important. Similarly, I can also use a F test. So I'm doing one after the other. I can do an F test, again the same. You give the X train and Y train, compute the correlation between, compute the extent of, so it's like a linear regression model that would be fit. And again, the P values are looked at. You could now see all the P values are less than 0.05. But again, we are seeing some values are greater than 0.05. So even these columns will get knocked out. All these are greater than 0.05. All these are greater than 0.05 and probably this one. So there are a few more variables that get knocked out wherever. So we can plot, we'll see that we are plotting the p-values, right? You could see I'm plotting the p-values based on the f-test. And so wherever the p-value is less than 0.05, I am retaining it. Wherever the p-value is greater than 0.05, I'm knocking it off. Probably if required, I can still call it as extrain only. Right now, you could see that these are the only columns that are remaining. Lump sum payment or not lump sum, that is one variable that is deciding. Then submission of the application to institution, negative amortization or not, loan type 2, debt to interest ratio is coming out, debt to income ratio is still coming out as an important variable. Loan to value ratio is still getting retained as an important variable. Co-applicant credit type EXP is one variable. Occupancy type PR is coming out as another variable. Property value is still there. Income is still there. So gender, sex not available is still retained. So possibly when people are not mentioning their gender, or when the gender is not available, probably there is some relationship with default. Credit worthiness, if it is L2, it is having some impact. And age-wise also, only the 55 to 64 group is having some kind of impact. So these are the two things that have come out. And probably I can still create. So if required, I can keep overwriting always. Probably I'll try to run this code once again so that I'll get a clarity on if I am going in the right direction or not. So this would be my final set of column. This would be my final set of column. Right now, let's not bother about PCA. I'll talk about the PCA later. So we are done with the feature selection mechanism. So this is where we can now get ready with the next steps, which is the feature transformation, possibly which we will do it in our next session. And from there, we are directly getting into the model building itself. So up to here, I think you can try the practice, and you can also tell me if there is any kind of error that is coming out, because somewhere underscore P versus without underscore P, I was trying to run the things. So you can see that up to here, a lot of variables should get released, should get removed, and only very few variables should get retained. And those variables are typically identified as some of the important variables in the overall process. Right? So I think I will stop this here. If anyone is having any kind of queries, I will discuss them. Otherwise, you should practice this. I'm not sure about how many classes I can take next week. I have some organizational related appointment in the next week for the whole of week. So I'll have to just plan. If possible, I'll take 1 or 2 sessions, but otherwise I'm not fully committing. So I'll have to work out on my schedule for the next week. But at least what you can very well do is you can pick up 2 or 3 different kinds of data sets in the meanwhile, and try executing until this feature selection mechanism. See how many features are getting retained, how many are getting knocked out through the various data sets, so that you will get a complete hold on the entire process. But I'll update you on how I can take, or if at all, if it is possible or not, I'll update you in a day or two. Okay. Thanks. So we are getting very close to building the models. So possibly we may try 1 or 2 models every class. Sometimes some small models, we can take them up 2 at a time also. But yeah, so just practice up to here. In case of any code issues or in case of any step that is not clear, you can very well ping me or you can put in the group and your friends or myself can typically try to answer them as such. All right. So I'll stop this here. I'll just wait in case.